This tutorial is about recursion, which is a powerful programming technique that can make some of your algorithms look very elegant. Before I introduce recursion, I would like to talk about the algorithm design paradigm that entails a recursive implementation. That design paradigm is called divide and conquer. You might have heard about divide and conquer in your introductory programming classes when you had to tackle a larger problem. But then divide and conquer was likely used in a very general sense, meaning you should first split the overall problem into smaller tasks, then solve the individual tasks and combine the solutions to solve the overall problem. For example, if you're asked to write an application that recovers JPEG files from a corrupt memory card, you may split the problem into the following subtasks. Designing and implementing a graphical user face might be the first one. Parsing the content of the memory card is another subtask. Writing an individual image to a file, and so on. If you look at those tasks, they are very different kind of tasks, and of course need to be solved by different algorithms. We use the more restrictive design paradigm divide and conquer, where the subproblems have to be of the same kind as the overall problem. So we still have the three steps: divide the problem into subproblems, but now the subproblems have to be all of the same kind. Conquer the subproblems. Since the subproblems are all of the same type, we can use the same approach to solve each subproblem. And finally, the combine step, to combine the solutions of the subproblem. For example, consider the problem of sorting a sequence of comparable values. A subproblem of the same kind is to sort a sequence of those values. Let's look at several problems that can be solved by divide and conquer. The problems we look at are the power calculation, binary search, and merge sort. We start with the problem of calculating the power of a value, where the power is a non-negative integer value. For example, we try to determine the value of 2 to the power of 8. We know that we can generally multiply 2 8 times by itself. But 2 to the 8 is also equal to 2 to the 4 times 2 to the 4. So we have divided the problem into the subproblem of calculating 2 to the power of 4. Now how do we compute 2 to the 4? Well, we just split this problem again into the subproblem of computing 2 to the 2, since 2 to the 4 is 2 to the 2 times 2 to the 2. In turn, 2 to the power of 2 is 2 to the power of 1 times 2 to the power of 1. And finally, 2 to the power of 1 is 2. Now we can combine the solutions of our subproblems. 2 to the 2 is 2 times 2, which is 4. Then we can compute 2 to the 2 times 2 to the 2, which is 4 times 4. Next, 2 to the 4 times 2 to the 4 is 16 times 16. And 16 times 16 is 256. So the final result is 256. An interesting observation is that we solved smaller and smaller subproblems again and again. It might look cumbersome, but we only had to perform 3 multiplication operations to determine the power of 2 to the 8. If we keep multiplying 2 by itself, then we need 7 multiplications. So the divide step of our divide and conquer approach here is splitting the power into 2 smaller values, n sub 1 and n sub 2, such that n sub 1 plus n sub 2 is equal to the original power n. The conquer step determines x to the n sub 1 and x to the n sub 2 as subproblems. Here's where recursion will come into play. Those subproblems are solved by the same process, meaning we split them up into even smaller subproblems and so on, until the subproblem becomes so small that it is trivial. In our case, that means if the power becomes 1. In the combine step, we multiply the two solutions of x to the n sub 1 and x to the n sub 2 with each other and get the final value of x to the power of n. Binary search is another problem where divide and conquer can be applied. In case of binary search, we are given a sequence of items. We are also given an individual item A and want to determine whether A is contained in the given sequence. If so, we want to access the item A in the sequence. The problem arises, for example, if you want to look up somebody's address. Let's say you have a list with names and corresponding addresses. The address list is sorted alphabetically by name. Now you want to look up the address of a specific person which plays the role of item A. Let's look at a simple example. Say we have a list of 7 names. As you can see, the names are sorted in lexicographical order. That means here in alphabetical order. We want to determine whether Lily is contained in the list. So a straightforward solution to the problem is to go one by one through the names of the list and check if a name matches Lily. In this case, you will have to step through almost the entire list to find Lily. If you are looking for a name that is not in the list, you will have to stretch through the entire list for sure. So in the worst case scenario, the runtime of this procedure is linear in the number of items in the list. Can we do better? As you may expect, we can do better by using divide and conquer. Note that we can quickly reduce the part of the list in which we need to search for, say Lily. We just take the name in the middle of the list, which is Jill. Obviously Jill is not equal to Lily, but since Lily is lexicographically larger than Jill, and since the list is sorted, Lily must be in the second part of the list, if it is contained in the list at all. So now we have to solve the smaller subproblem that requires to search for Lily in the list consisting of the last 3 names. We apply the same process to the sublist. We take the element in the middle of the sublist. In this case, it is Lily, and we detect that this is exactly the name we are looking for, so we are done. Let's say we are looking for the name Greg. The original problem requires to search in the entire list. We would compare Greg with the name in the middle of the list, that is Jill. Since Greg is lexicographically smaller than Jill, we continue searching for Greg in the first half of the list. So we have reduced the original problem to a subproblem. Again, we try to split the subproblem into an even smaller problem. We compare Greg with the name in the middle of the sublist, which is Bob. Now Bob is lexicographically smaller than Greg, so if Greg is in the sublist, it must be to the right of Bob. Therefore, the size of the sublist is reduced to a single name, in this case Don. We compare Don with Greg, and since the 2 names don't match, and since there are no other names in the sublist, we can conclude that Greg is not in the sublist, and not in the original list. The divide and conquer steps of binary search are as follows. In the divide step, binary search determines the half of the sequence that may contain the item we are looking for. The conquer step determines whether the sought after item is contained in that half of the sequence. The combine step is simple. If the sought after item is found in the subsequence, it is returned. If not, it is not contained in the original sequence. If we want to implement binary search, we have to decide on the data structure that stores the sequence of items to be searched. An array is most suitable since we need to access items at a particular position. The use of indices allows us to calculate the position of the item we need to access. Here's a high-level pseudocode for binary search. First, compare A with the item in the middle. If the item in the middle is equal to A, then stop and return that item. If A is smaller than the item in the middle, perform binary search in the first half of the array. If A is larger than the item in the middle, perform binary search in the second half of the array. If the array contains only one item, then stop because the array does not contain A. In the last example of divide and conquer, we look at merge sort. The task demands sorting an array of comparable items. We have seen already different solution algorithms for sorting, like insertion sort or bubble sort, for example. The time complexity of each of these elementary sorting algorithms is quadratic in the worst case. We will see later on that the time complexity of merge sort is better than quadratic time, even in the worst case scenario. The idea of merge sort is as follows. Assume you have 2 sorted arrays and you want to create one sorted array that contains the elements of both sorted arrays. This task is not very hard. We can look at the first element in both arrays, which are 1 and 2 here. The smallest of the 2 elements must be the first element in the new array. So we copy 1 into the new array. Then we compare again the two elements at the front of each array that have not yet been copied into the new array. So we compare 2 with 4. Again, the smallest of the two comes next in the final array. Then we compare 4 and 3. And 3 is copied into the new array. Now we compare 4 and 6. So 4 is copied into the new array. We compare 8 and 6 is copied. We compare 8 and 7 is copied. Now all the elements of the second array have been copied to the sorted array. So now the remaining elements of the other array are copied right into the new array. So merge sort splits the original array into two halves and sorts each half separately, and then merges the two sorted halves together using the same process we just saw. Each half is sorted by the same process. That is, each half is further split into half and so on. We stop splitting a subarray into halves if it consists of a single element only, since an array with a single element is trivially sorted. So in the divide step, merge sort divides the array to be sorted into two halves. In the conquer step, two subarrays are sorted by splitting the subarray into smaller and smaller parts until sorting becomes trivial. That's when the array consists of one element only anymore. In the combine step, the two sorted subarrays are merged into one sorted array. The pseudocode of merge sort takes only a few lines. Let's say we have a method merge sort that gets as input an array, say array data, and it also gets the index of the first element, that index is called low, and the index of the last element in the array, that index is called high. The two indices are necessary when we apply merge sort to a subarray. If the array contains only one element, then the index of the first and last element are the same, that is low is equal to high. In this case, the array is trivially sorted. Otherwise, we split the array into two halves. In order to do so, we determine the index of the element in the middle, which is the sum of low and high divided by 2. Now we call merge sort for the two subarrays. The first subarray goes from index low to mid, and the second subarray goes from index mid plus 1 to high. In the end, the two subarrays need to be merged together using the same algorithm we have looked at before. Observe that the procedure calls itself. That is exactly what is called recursion. We will have a closer look at recursion in the next part. We call merge sort where we split an array into half and solve each half by calling merge sort again. That is an example of recursion. Recursion is a programming technique where a method or function or procedure calls itself directly or indirectly. Let's start with a simpler example than merge sort to understand how a recursive method is executed. The method countdown has one integer parameter called count. The method should print the numbers starting at the parameter value count and counting down until 0 has been reached. If, for example, countdown 2 is executed, then the values 2, 1 and 0 should be printed. In that case, countdown 2 first checks if count is greater than or equal to 0. Then count, that is 2, is printed. In the next instruction, count is decremented by 1. And now countdown is called with value 1. There's actually nothing very special about how this method call is executed. It is handled like any other method call, only this method call happens to be a call to the same method as the method from which it is called. So now countdown is executed with count equal to 1. The expression in the if statement is evaluated, that is, count with value 1 is compared to 0. Then the value of count, that is 1, is printed. Then count is decremented to become 0. Now countdown is called again. In this call to countdown, the parameter value is 0. Since count is still greater than or equal to 0, Count is printed, in this case 0. Then count is decremented to become -1 and countdown is called again. In this call to countdown, the condition will be false, so the method directly terminates, and one by one the previous method calls are terminated. Now let's modify this procedure to print the number starting at 0 and counting upwards until count is reached. If count_up true is called, the method is expected to print the values 0, 1 and 2. In the first call to count_up, count is 2, so the body of the if statement is executed and method count_up is called with argument value 2 minus 1. Note that the first method call is not yet completed and the method will finish after the second method call to count_up has been completed. Do not get confused about the value of the parameter count. Each method keeps track of its individual value of the parameters and, if there are any, of local variables. Whenever a method is called, imagine that the method creates a new copy of the method with all its parameter and variable values. So the first time we call count_up, we keep track of the specific information for this method call. When this method call reaches the call to count_up, another fresh copy of count_up is made where count has value 1 now. When the method call to count_up is reached, the value 1 minus 1, that is 0, is passed to the method. So a new copy of this method is made where count is 0. Now the third execution of count_up starts. Note that each execution of the method starts with the first instruction of the method, that is with the if statement in this case. Since count is 0, the body of the if statement is again executed. When the call to count_up is reached, a fourth fresh copy of the method is made where count has value -1. The condition in the if statement is false in this case, since count is not greater than or equal to 0. So this method call terminates and execution continues at the point where the terminating method was called from. Since that method call is now done, the next instruction, print count, is executed. Note that count has value 0 in the current method call and therefore 0 is printed. The third method call to count_up is done now and execution continues at the point where the method was originally called from. As that call is done, print count is executed and therefore 1 is printed. The method call with parameter value count equal 1 is done and execution continues at the first call to count_up. That call continues at the print instruction and prints 2. Now we are finally done and have printed the values 0, 1, 2. The information that is maintained for each method call is called an activation record. Whenever a method is called, an activation record is created that records the values of the local variables and of the parameters. It also keeps track of the instruction that is currently executed. The operating system creates these activation records. The programmer has not to be concerned about those records. There can be many active method calls at any point in time where a method call is active if that method call has been made but the called method has not yet been completed. The operating system stores all activation records of active methods in one collection. In particular, the operating system uses a stack to store the records. This stack is called the call stack or activation record stack. Why using a stack? Well, because if a method terminates, execution continues with the most recently made method call. By using a stack, execution continues always with the method call whose activation record is on top of the stack. That is the method that has been called most recently. Remember the second example, count_up? Observe how the activation records are added and removed from the same end. We will go through some examples that show how recursion can be used. The first example is the method countdown from before. The method first prints count, decrements count by 1 and then prints the remaining numbers counting down to 0. As the recursive call is made at the end of the method, this application of recursion is called tail recursion. If, for example, a call to count down 2 is made, the method prints the numbers 2, 1, 0 in that order. We use the method countup as a second example. Here the recursive call is made at the beginning, before count is printed. This form of recursion is called non-tail recursion. So first, the numbers 0 to count minus 1 are printed in the recursive call, and then finally count is printed. For example, the call to count up 2 prints the numbers 0, 1, 2. Let's look at the role of the if statement in the method countdown, for instance. Assume we do not check whether count is greater than or equal to 0. What will happen if we call countdown 2? As before, the values 2, 1, 0 are printed. The call countdown 0 will make a call to countdown minus 1. Note that the recursion does not stop at this point. Countdown minus 1 will print minus 1, and countdown minus 2 will in turn print minus 2, and so on. This process will never terminate. If you implement this method in, say, Java, and then you run this faulty method, then the call stack with the activation records will eventually run out of memory, and you get an error message saying something like stack overflow. We need a stop criteria that terminates a sequence of recursive method calls. This scenario at which the method will not make another recursive call is the base case. In the given example, we need the if statement that checks if count is greater than or equal to 0. In turn, if count is less than 0, then no recursive call is made, and in this example no further instructions are executed. So the base case in this case is where count is less than 0. In summary, the base case is a case in a recursive method that is solved without a recursive call. Every recursive method needs a base case, otherwise the method would cause an infinite sequence of method calls. Let's look at another example. It's a standard example you will find in virtually every textbook. That is a calculation of factorial. The factorial of a natural number n is basically the product of the numbers 1 to n. For example, 3 factorial is equal to 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is equal to 24. 1 factorial is equal to 1. The definition of factorial is as follows. 0 factorial is defined to be 1. For numbers greater than 0, factorial is defined by a recurrence relation. N factorial is equal to n minus 1 factorial times n. If we again compute 3 factorial using the definition, then 3 factorial is computed by 3 minus 1 factorial times 3, which is 2 factorial times 3. 2 factorial is 2 minus 1 factorial times 2 according to the definition. So 3 factorial is equal to 1 factorial times 2 times 3. 1 factorial is 0 factorial times 1. So 3 factorial is equal to 0 factorial times 1 times 2 times 3. Since 0 factorial is 1 by definition, 3 factorial is 1 times 1 times 2 times 3, which is 6. Now we want to write a method that calculates the factorial of a number passed in as a parameter. Let's call the parameter n. The definition can be translated directly into code. If n is equal to 0, then the result is 1. Otherwise, the result is n minus 1 factorial times n. You can imagine why factorial is such a popular example for recursion. Its recursive definition lends itself directly to a recursive implementation. Here's another example of a recursive definition, the Fibonacci numbers. The Fibonacci numbers are a sequence of numbers where each number is calculated as a sum of the two preceding numbers. The first Fibonacci number, f sub 0, is defined to be 0. The second number, f sub 1, is defined to be 1. The following Fibonacci numbers, f sub n with n greater than 1 are defined as the sum of f sub n minus 2 and of f sub n minus 1. For example, f sub 2 is equal to f sub 0 plus f sub n. Since f sub 0 and f sub 1 are 0 and 1 respectively, f sub 2 is equal to 1. F sub 3 is equal to f sub 1 plus f sub 2. By definition, f sub 1 is 1, and we just calculated that f sub 2 is 1 as well. Thus f sub 3 is equal to 2. F sub 4 is f sub 2 plus f sub 3. Since f sub 2 is 1 and f sub 3 is 2, f sub 4 is 3. Try to calculate yourself f sub 5. You should get 5. Now let's develop a recursive method that receives as parameter the subscript of the wanted Fibonacci number and returns the value of that Fibonacci number. For example, if the method receives as parameter value the value 4, it should return the value of f sub 4, which is 3. We call the method Fibonacci, and the parameter name is n. The Fibonacci numbers are only defined for subscripts n greater than or equal to 0, so we require that n is greater than or equal to 0. Recall the definition. If n is 0, method Fibonacci should return 0. If n is 1, the method should return 1. Thus for n equal to 1 or 0, we can return the value n. Otherwise, the definition defines f sub n to be the sum of f sub n minus 2 and f sub n minus 1. Thus we recursively calculate f sub n minus 2 and f sub n minus 1, and then the method returns the sum of the two values. Now watch the activation record stack when we make the call to Fibonacci 5. That looks ridiculous. Could you see how the same method calls are made repeatedly? To determine Fibonacci 5, we only need to compute the preceding Fibonacci values f sub 0 to f sub 4, and each time the next value can directly compute it from the preceding two values. That are basically 5 steps. But our recursive solution keeps going on and on, recalculating the same value again and again. The truth is, a recursive solution to the Fibonacci numbers is very inefficient. It is not the way to go in this case. What happens here is called excessive recursion, since the same subproblems are computed repeatedly. An iterative solution is much better. Look at this method that solves Fibonacci iteratively. As you can see, this method is linear in the value of n. Our recursive try has actually an exponential runtime. I wanted to return once more to divide and conquer. We call the 3 steps consisting of divide, conquer, and combine. I would like to add a step 0, which constitutes a base case. If a problem is so small that it cannot be split up into subproblems anymore, then it is solved directly. Often the problem is trivial if it is very small. In the conquer step, we can solve the subproblems by recursive calls. For example, in the case of merge sort, remember we split the array into half and sort each half separately. But if the array contains a single element only, we cannot split it further into smaller subarrays. Instead, we sort the one element array directly. Luckily, that is trivial because a single element array is sorted anyway. So there's nothing to be done. And as you can see, if the parameter value low is equal to high, that is, if the first and last element in the array to be sorted is the same, in other words, there's only one element in the array, then the method merge sort does not execute the body of the if statement. Instead, it directly returns. This is a base case of merge sort. The conquer step is implemented by the 2 recursive calls to merge sort. So recursion can be applied if we can split a problem into subproblems of the same kind, like we do when applying divide and conquer. A recursive solution is often very simple and elegant and easy to understand. But recursion is not always the best option. Indeed, every recursive solution can be implemented iteratively. An iterative solution is often more time efficient than a recursive one. In particular, if the same instances have to be solved again and again in multiple recursive calls, then recursion is not a good choice.